right, so our second speaker today is Daniel Faraco, and he will talk about geometric function theory, Burkholder functionals, and lower semicontinuity. So please.
Okay, so thank you, Mario, and thanks, Yanni, for his great talk. Actually, I know you guys know, but we were students together in UASC. It's scary to say more than 20 years ago, and it's very nice to see the beautiful mathematics he's doing these days. So I'm going to talk about something actually that I started to think about at those times, like 25 years ago. And okay, we have now made some progress also based on some important work of Asta, Prause, Ivanik, and Saxman. And that's what I would like to report here. So since I'm not aware, so this is mixing a bit ideas from quasi-conformal mappings and from the vectorial calculus of variations. So I will try to be basic in both, but communicating at the same time a number of ideas. And maybe the punchline is that the story of factorization, which was also important at Gianni's talk, it's also very relevant in the issue of lower semicontinuity for integral functions. And that's somehow something that we probably should have been aware 20 years ago, but we have realized just last year. Okay, so let me start with Morrey's definition of quasiconvexity, which is something that he coined in the early 50s, and it's a definition to understand minimization problems in the vectorial calculus of variations. So I just mentioned the definition is that you are considering deformations, so maps from Rn to Rm, and then there is linear maps, so given by constant matrices, and then quasiconvexity says that the corresponding energy, the corresponding integral, is minimized by the affine boundary values. So here we see it. So we have that f of a minimizes integral of f of a plus t of h, where h at this moment is a C0 infinity function, that is to say is compactly supported. And okay, this is a very general definition, and let's say that people working in geometric function theory, we would be very happy if one functional was quasi-convex. And this is the so-called Burkholder functional, which is here. And it actually makes sense in all dimensions, but in dimension 2 is this type of weighted norm where the determinant is involved. And there is a Burkholder functional for every exponent p from 1 to infinity. And if p is equal to 2, we get back the usual Jacobian determinant. And I would say it's sure an analysis paper if you guys are able to show that the Burkholder functional satisfies this inequality posed by Morrey. And I will explain why in a couple of slides. But actually, the reason why Morrey introduced this notion of quasi-convexities was to be able to run the direct method of the calculus of variations. The direct method of the calculus of variations essentially says that if you have a functional who is weakly lower semicontinuous with respect to sequences, that is to say, if I have a sequence phi j which converges to phi weakly in some topology, let's say in W 1 infinity, then the image has less energy than the image of the energy of the sequence. And therefore, if this sequence was converging to the infimum, then the image is a minimum, and we have found a minimizer of our variational problem. Okay, and it's actually very easy. Okay, this is working. Good. It's not difficult to go from Morrey's definition to this over semicontinuity. So let me give you the argument. Suppose that d phi j, this easy case. Okay. D phi j converges weakly to A. then I cannot apply directly the definition of Morrey, of quasi-convexity, because the phi j has not affine boundary values. But what I can do is take my domain and then take a cutoff function, so I want to put this and then put something here, eta, which is identically equal to 1. And then consider phi j equal to eta phi j theta, eta phi j plus 1 minus eta ax. So at this, because eta is 0 at the boundary, then this new phi j theta will have this a as boundary values. So therefore I can plug it in the quasi-convexity inequality. And then the game is to make that this region is smaller and smaller. Okay, and okay, eta will depend on a parameter k, and you have to be a little bit careful. But it's a good exercise to show that with this idea, quasi-convexity implies over semicontinuity, at least if I know that the unit map is constant. And in other case, one can do a localization. So in fact, Morrey's definition was almost tautological. But I want you to keep in mind how to go from quasi-convexity to lower semicontinuity, and it's by modifying my sequence in the neighborhood of the boundary by means of a cutoff function. Okay, and that's what you typically do, and that was what Morrey did almost 30 years ago, 70 years ago. Okay, in one dimension, quasi-convexity is convexity, and in higher dimensions, there are examples of classical examples of non-convex functionals, and the main guy is the determinant, which is a null Lagrangian, and therefore it satisfies actually the quasi-convexity inequality with inequality. Okay, so there are examples beyond convexity, and there has been an effort to try to understand what on earth are these quasi-convex functionals and how far they are from convexity. And a necessary condition is that if f is quasi-convex, is convex in rank 1 directions. And that's, again, not very difficult. So rank 1 directions means that A minus B, A is a matrix and B is another matrix. And I say that the difference is a rank 1 if A minus B is a rank 1 matrix. In other words, the rank of A minus B is equal to 1, and if we would be in 2 by 2, the determinant of A minus B is equal to 0. And then to be rank 1 convex means that if I look at this function, f of c plus t of A minus B, C is another matrix, A minus B is the rank 1 matrix, and then this is a function now of one variable. From t, I go to this, and this is convex. So it's convex in some specific directions. And how do you prove this from Morrey's definition? Well, you can create, because A minus B, they are only different in the direction to n, you can create a sequence, an explicit sequence, so that d is gradient, takes values essentially A, B, A, B. Okay, and then when you put them there in this gradient in the quasi-convexity definition, then you get a rank 1 convexity. And there are more examples, and the question of the area, what is called now by the name of Morrey's conjecture, is whether this is an if and only if condition. So whether this quasi-convexity implies rank 1 convexity, but whether rank 1 convexity implies quasi-convexity. And that would be much better, because quasi-convexity is a crazy definition, because we need to test with infinitely many test functions. And that's not very practical, but rank 1 convexity being still complicated, it means just that you are elliptic in certain directions. And for example, if the function was smooth, you could test whether the Hessian is positive in those rank 1 directions. And it's not true if the target domain is three-dimensional, but it's still open in dimension 2 by 2. Okay, so the Morrey's conjecture is whether rank 1 convexity implies quasi-convexity. And the example I started with, the Burkholder functional, has the nice feature is that it's rank 1 convex. So if Morrey's conjecture was true, the Burkholder functional would be quasi-convex. There is a lot of partial results. Let me skip them. And okay, because as you saw, the Burkholder functional is pretty simple. It has a lot of symmetries. So we will be happy to show that, okay, suppose it's rank 1 convex and it has some additional symmetries. Is at least then quasi-convex? And then another interesting issue here is that the quasi-convexity definition makes sense in many scenarios, but this is re-arising from models in what is called hyperelasticity, which postulates that you have an elastic material, there is an energy functional which is defined by the crystalline structure of the material, and then the deformations that you can make are really the minimizers of your variational problem. And somehow we would like that quasi-convexity, instead of having a proof, an abstract proof, it's consistent with those restrictions, which I will be more specific later on. Okay, so here is back our friend, the Burkholder functional, which is rank 1 convex. If you look at it a bit more carefully, it's homogeneous and it's isotropic. If instead of A, I consider a tilde, which is RAQ, where R is a rotation and Q is a rotation, then I get the same value. So you cannot ask more, right? It's homogeneous, it's isotropic. So at this then we should be, and it's rank 1 convex, at this then we should be able to prove that this one function is quasi-convex. And actually this, the name of Burkholder is rightly there because he introduced it in his study of martingale inequalities, and and then it appeared again in the quasi-conformal theory, because if you remember, or if you are aware of it, there is the unique singular integral in the world with holomorphic kernel, which is the very null force transform, has the property that maps fz derivatives to fz bar derivatives. And we would like to know what is it's a p-norm, and that's the conjecture of Tadeusz Iwaniec. And it turns out that this would come as a corollary from the quasi-convexity of the Burkholder functional. And this is because the Burkholder functional gives you a lower bound for this pointwise lower bound for this expression. So if it was quasi-convex at 0, this integral would be greater than 0, and therefore this integral would be greater than 0, and then we could move the f set to the power p to the left-hand side, and we would have a proof of Iwaniec's conjecture. Okay, so it's even better if one proves the Burkholder, the quasi-convexity of this one function at 0, then you have already the precise AP norm of the very null force transform. Okay, and we expect that actually then from the proof we will get some ideas on what you can do in higher dimensions. Okay, so we have on one hand this notion of quasi-convexity, this integral condition, which implies rank 1 convexity, which is a local condition. We would like that rank 1 convexity implies quasi-convexity always for 2 by 2 deformations. But if not, we are happy that it happens for functional with symmetries. And if not, we will be happy that it happens for this one functional, which is the Burkholder function. Because if that was quasi-convex, then we would have solved Iwaniec's conjecture. Okay, so I would like to present a theorem which says that, yeah, it's quasi-convex, but this we don't know how to do, not yet at least. But at least we made some progress recently, and is that we can consider a local version of the Burkholder functional. This functional has, as you can see, has positive and negative values. So actually, I can let me do a cartoon. So it's clear that I shouldn't become a drawer. As job. Okay, so this is a cartoon of all 2x2 matrices. But I am just drawing a diagonal matrices. Okay, so this is 1, 1, 0, 0, and this is 0, 0, 0, 1, and this is here, and this is here. So this quadrant here means that the determinant is positive, x, y is positive, and here is also positive, and here is negative, and here is negative. So one can show, and it's that the Burkholder functional is negative on a cone, which is a subset of the matrices with positive determinant. And what we can prove is that if you declare a new functional, which is equal to the Burkholder functional in this cone, and immediately when it gets positive, you give it the value plus infinity, that's quasi-convex in the Morrey sense. Okay, so this is a partial result about the quasi-convexity of the Burkholder functional, and it has another interesting implications. Actually, we can prove a little bit more, which will be clear at the end of the talk. Is close quasi-convex. This means that it's quasi-convex for gradient measure. And before you know what this is quasi-convex for sequences. Okay, and it is interesting. Let me go back to this picture. So we have shown that here is quasi-convex in its negative part. So we could look at the complementary situation when we are restricting our Burkholder functional to matrices where it's positive. There is even better. Then it's a polyconvex. That's a result of that's a point-wise characterization actually, and it's a result of Guerra and Christensen. In particular, it is quasi-convex. So it is quasi-convex when we restrict it to these positive values, and it is quasi-convex when we restrict it to negative values. But we don't know. Maybe this requires an explanation. So the definition is like this. This is what I would like to show. Whenever h has 0 boundary values. Now, what I am saying is that if a plus dh at almost every x satisfy that BP is negative, this inequality is true. And if a plus dh satisfies that this BP acting on it is always positive, then the inequality is true. What I don't know what happens is that if I have a deformation that takes values sometimes here, sometimes here. That's an exercise for the audience. Okay, good. And interestingly, the proof uses the fact that the function is isotropic very strongly, but so it uses that it has some symmetries, but it could have another symmetries. For example, in a very interesting work, the same authors, let me tell them, Asta, Prause, Ivanik, and Saxman, they study a complex version of the Burkholder functional for understanding how biaxial maps can rotate. And that functional, it has another invariance. So it has is invariant if we have conformal matrices which are in a logarithmic spiral. I think that if beta is equal to 1, then I recover SO2, and then I will be having the isotropy I was mentioning before. And if beta is in a complex number, then this is a group of conformal matrices, and I can always ask that, okay, my new functional B times R1, A, R2 is equal to B of A, where R1, R2 belong to the logarithmic spiral. Yes, to look. And then these symmetries are also enough to prove quasi-convexity. Okay, so in a sense, at this moment of the talk, at least what I am presenting is a way to prove quasi-convexity for certain functions which has some additional symmetries. Okay, just to connect it with Gianni's talk, what is this zero set? Well, this zero set is recall that the Burkholder function it was this expression with a weight, so it's going to be negative if and only if this expression is negative. But then we can do the algebra, and we get that the differential is controlled by k times the Jacobian, and that's something we have seen in the previous talk. That's the definition of quasi-regularity, which in the plane is just our love vectorial equation. Okay, so to look at the zero set of the Burkholder functional is to look at quasi-regular mappings. Then later on there will be quasi-conformal mappings with a precise relation between the exponent p, which was characterized in my Burkholder functional, and the k. So the distortion k has to be exactly equal to p over p minus 2, or p equal to 2k over k minus 1. And then for specialists about higher integrability, they will recognize this is precisely the threshold of higher integrability of k quasi-regular maps. Okay, good. Since I am typically considering affine boundary values, that's enough to impose that with this, and the determinant is positive, that these guys satisfying this pointwise inequality, and with these affine boundary values, they are homomorphisms. So therefore, my test functions are going to be k quasi-conformal maps. So another way to interpret our results is to have a sharp quantitative higher integrability theorems for k quasi-conformal maps. Okay, it's going to be very important, maybe at several points, but even more at the end of the talk, what are called principal quasi-conformal maps. So looking at maps, solutions to the vectorial equation, quasi-conformal maps from the plane to the plane, and I want to prescribe the behavior at infinity. And then classical principal maps, they are like Z, and then they have a Lorentz series, and okay, those are principal maps. And think that, for example, if I have in the unit disk this map, which is Z plus A1 Z bar, then I can apologies. So this is Z plus A1 Z bar, and then I can continue this because Z bar at the boundary of the unit disk has the non-trivial feature for us that is equal to 1 over Z. And therefore, I can make this is a continuous and well-defined principal map. So it's Z plus A1 Z bar inside the unit disk, and Z plus A1 over Z at the complement of the unit disk. Okay, that's a very naive principal maps, but already it's gonna it will be important to show that our estimates are really much stronger than quasi-convexity. And it's customary in geometric function theory to normalize so that f of z is equal to z at infinity. But since I want to consider any affine behavior, then I will be talking about A principal maps, and then that's simply to say that I have my Eulerian series start with A0 Z, and then plus A1 over Z plus A2 over Z. And instead of A0 equal to 1, okay? And that I call A principal, okay? Maybe warning about notation. So a 2 by 2 matrix, A, can be understood as A0 Z plus A1 Z bar. Okay, this is what we do typically for the differential, and A0 will be the dz of f, and A1 it will be the dz bar of f, But if you do this for a linear map, then you have complex coordinates for a matrix. So a matrix A can be identified with these two complex numbers, A0 and A1. Okay, good. So that was for the Burkholder functional and for the interest in the AP norm of the varying transform, and then what we could say for quasi-conformal maps. But then actually, as I was briefly saying at the beginning, all this business of quasi-convexity and polyconvexity restarted when John Boyle discovered in the late 70s that there were many real materials in hyperelasticity that could be modeled by these functionals, which were quasi-convex but not convex, and that's why I changed it a bit later. And okay, so I'm studying deformations from the plane or from the space to the space, and what I don't want is that these deformations that the matter penetrates. So I really want to consider the case where my deformations are one-to-one, and at least I want them to be one-to-one locally, so the determinant has to be positive. So typically in elasticity, this thing that we are doing, that I was doing here, if you remember, of putting infinity outside of a set, is typically done outside of the set of matrices with positive determinant. Okay, and a typical is actually been studying quite a lot of engineering in the last couple of years, and you would like to make something quantitative. So you would like that this energy of A goes to infinity as the determinant goes to 0. So this would be a typical landscape. So this would be this, and then it goes. So it blows up as soon as the determinant goes to 0, which are these lines. Okay, remember that I am with my cartoon, which is the diagonal matrices are all matrices. So in particular, these two x's represent the 0 set of the determinant, and that's what you typically want. Okay, but how this should be done is a question, because this is really beyond the things they can test with stress and strains. So it's more a postulate. And one of the messages I want to get through is that perhaps exactly mappings of integrable distortion are the right class of mappings to study these deformations. Anyhow, so there is a lot of mathematicians and engineers dealing with this type of energy functionals. And then one that was in the literature that was sort of relevant is this functional, which is it's called W, and here is what we typically call K in the quasi-conformal world. This is the logarithm of K. This is the logarithm of the determinant. And it has this what they call asochoric volumetric speed. Volumetric because there is this part of the determinant which penalizes volumes. And then this is isochoric in the sense that it's really a function of A divided by the determinant. They give it this name. Okay, and it has this feature that as the determinant tends to 0, then the W blows up. Okay, and then it's defined in the complement of for matrices with positive determinant and infinity elsewhere. Okay, so if you take our arguments to the image, you can show that this function is quasi-convex, and that's been very bad with numerical analysis. I was very happy with this because there were some numerical experiments saying that this was not quasi-convex. So for once, theory beat it numerics, and it's a rank 1 convex and it's quasi-convex. So we were very happy, but then and then also the reason because these fellows were interested in that is that at least it gives a positive answer to Morrey's conjecture in some cases. So if F has this isochoric volumetric speed and H is convex, which is one of the cases they consider, then for such a functional rank 1 convexity implies quasi-convexity. So This, after all these many years, we have an instance where the answer to Morrey's conjecture. And that's satisfactory, but then there is a big issue. Remember that I was explaining that the only reason that Morrey had to introduce quasi-convexity was to describe energy functions which were over semicontinuous and find minimizers. Okay, and probably I went very fast, but I said under growth conditions. Again, sorry, this fancy pen has this problem. So I said under growth conditions. Okay, let me try it once more. Under growth conditions, quasi-convexity is equivalent to sequentially weak lower semicontinuity. And I gave you a proof, and then I sweep under the rug under growth conditions. Now, if I have this feature that is required in elasticity, that the energy blows up as the determinant goes to zero, then this is inconsistent with the growth conditions. So the growth conditions for which Morrey's theorem applies are inconsistent with these models in elasticity. And the first problem in the list of open projects of John Boy in the 80s about the nonlinear elasticity and its mathematical theory was to understand whether quasi-convexity or another condition would give a sequential weak lower semicontinuity under this hyperelasticity condition. That is to say that the energy blows up when the determinant goes to zero. Okay, so in a sense, I was cheating. First, I presented that quasi-convexity characterized sequentially weak lower semicontinuity. I was given a number of theorems where we prove that certain functions were quasi-convex. But then I am being more honest and I am saying, okay, but in this situation, this quasi-convexity does not imply sequentially weak lower semicontinuity. Okay, and that's very good for how to call it, function theoretic geometers as we are, or as people interested in geometric function theory, because then I recover my definition of a principal map. Recall that F is a principal if A has this development A0, there's A1 over Z, there's many things, AN over Z to the N greater than 2 at infinity. And so if you think that this is very small, this is to say that F is like A of Z at infinity. Not quite, but okay. And in the boundary of the unit disk, F is equal to A of Z plus the trace of this part. So in particular, if A would have affine boundary values, it would be a principal quasi-convex in this setting where A2, A3, A4, all of them would be zero. So we require that the quasi-convexity inequality holds for those. Okay, so we take this A, which is here in the Lorentz series of F, which is the behavior of our homomorphism at infinity, and we require that the same quasi-convexity inequality, so the action on the linear map minimizes the energy respect to all principal maps. So it's stronger than quasi-convexity, but it's not very natural from the geometric function theory viewpoint. And okay, first you can show that both BP and WV are principal quasi-convex, and there are many others. Many polyconvex functions are principal quasi-convex. But for example, this typo here, the determinant is not principal quasi-convex. So minus determinant is determinant not. Okay. So it's not true that all quasi-convex functions are principal quasi-convex, but many of them are. And the good news is that if you have this principal quasi-convexity which is consistent with these notions of hyperelasticity, and you are dealing of mappings with whose distortion is in A1, then there is a sequentially weak over semicontinuity. Okay? So this gives an answer at least to the, if not the answer, an answer to this question of John Boyle in dimension 2. So this is, of course, n equal to 2, because I cannot even talk, well, at least not the way I wrote it, I cannot talk about principal maps. And surprisingly is also, so we have this condition K in A1, but it turns out that this, what we define like mappings of asymptotically finite distortion, that is to say that point-wise the limit is finite, no integrability conditions whatsoever, then you also get a lower semicontinuity. Okay, so if you are tired at this moment, think about the K in A1, but just for a specialist, which I thought, I was completely sure that this was the only case where we could get a lower semicontinuity, but somehow the proof also works with this somehow a strange condition. Okay, and yeah, and okay, this might seem that this is very special, this principal quasi-convexity, but typically all these functions which has, for example, this isochronic volumetric speed, then G will be something F which is polyconvex, and another which is a Q principal. So there are many materials, and okay, I guess I assume at least that this audience is not that expert or maybe not that interested in elasticity, but in this classical book in linear elasticity, it is explained how this type of deformation, which are called plane strains, are modeled with these two-dimensional problems. And this is something I was very surprised to discover. So typically in elasticity, one considers this thing, and this has is the second invariant. And look at it. It's just the distortion plus 1 over the distortion. And they typically assume that, okay, let's assume that our deformation satisfies that this is finite. So this is to say that K of d phi is finite. Okay, this is, sorry. So that's to say that to assume that we have a theory for mappings with integrable distortion is quite consistent with the requirements. So I typically postulate these questions for specialists, and of course, I don't know. Maybe it is the case that for at least for planar deformation, you don't want to have something whose determinant is very small, but you want to allow that the deformation has a small determinant in some regions of your domain. It could be that K in A1 is the red condition, but this for the mathematical theory, it is the red condition. Okay, so that's what I want to say somehow. Principal quasi-convexity is a lower semicontinuity. And okay, I will be explaining part of the proof of the quasi-convexity of the Burkholder functional, but let me tell you this argument. Recall I was explaining that how quasi-convexity was given a lower semicontinuity, and it was by modifying my sequence near the boundary. You recall I was doing this, and given phi j, I was having phi j tilde, which was this interpolation between phi j and the affine boundary values. What's the problem of this strategy in this setting is that you will ruin the determinant being positive, and therefore, since your functional is infinity when the determinant is negative, and then when you do this trick, you are done. So you cannot do this trick, and therefore, it's not clear why quasi-convexity would imply lower semicontinuity. Instead, what a good a good quasi-conformalist would do, as Gianni was explaining to us, is do a story of factorization. So I would have my deformation, and I would factorize it as an holomorphic part and a principal map. A principal map I deal with almost by definition, because principal quasi-convexity is done for the principal map. And the holomorphic part has this feature that typically with a small bounds, weak convergence will imply a strong convergence. Okay? Hj prime will converge strongly to Hj. This it may be more precise, local uniformity. Okay? So once you come to the idea, it's not crazy that you can do the same trick I did, replacing phi j by this phi j tilde, trying to replace my original sequence with the principal map, because the Hj is holomorphic, and I know I have a lot of tricks to work with it. Okay, that's the reason why at least one can expect that such theorems will be true. And okay, last word in the introduction. I was typically saying, okay, suppose that if I have this energy, f of d phi, and then I want to understand its lower semicontinuity. And typically in the theorems, I was going quite fast, but I assume that this quantity is equi-integrable. That is to say, because if it's equi-integrable, in other words, it converts weakly to something. Okay, so I have enough conditions of the functional and the functional so that this converts weakly to something. Then I have lower semicontinuity. But we would prefer that this is not a requirement, but this comes just from the assumptions on the distortion. And indeed, for many cases, if k is in A1 plus epsilon, then there is this estimate that I think the first version was proved by Gianni and Koste, and then together with Raja, they improved that the distortion controls the logarithm of the Jacobian. But if you remember, for example, in W, there was this term logarithm of the Jacobian, and this reappears in many materials. And therefore, if I have this k plus log of k minus log of the Jacobian, and k was in A1, then this term would be good, this term would be good, and this term would be good thanks to this Koske-Laoninen estimate. And we would like to know whether this is true at the level of equi-integrability. That's probably one good question for Gianni. This we don't know. And finally, anyhow, we would like to have this lower semicontinuity theorems without assuming equi-integrability. And then we went back to the Burkholder functional, which we look at it carefully in the last year, and then so from quasi-convexity, you have an immediate a theorem of lower semicontinuity if you assume that the sequence is a little bit more integrable. Remember, I have d phi j converts weakly to d phi in W1P, and I would like to prove that this the inf is greater than the integral of pp of d phi. This is lower semicontinuity. So I can prove it if the convergence is directly from lower semicontinuity, from quasi-convexity, if I have a little bit more of integrability. A more complicated argument tells me that it's enough actually that the limit map it's in W1P. And what maybe is more surprising is that this has bit growth, right? So this is BP, as I said, is P homogeneous. So this is like the AP norm. Okay, or is this controlled by the AP norm? If I have a convergence in W1P, then I can control the AP norm, but the AP norm is, the bit power is just in A1, and therefore it does not necessarily have a weak limit. It could converge to a measure, okay? However, what we prove is that this BP of d phi j this is equi-integrable, and that's and which shouldn't be. So that's to say that there is a sort of higher integrability, and typically, as we know that if the Jacobian, if we have a map in W1N, the Jacobian, which a priori should be in A1, then there is the famous result that is in A log L. Then something similar happens with the Burkholder functional. We have a higher irregularity in this equi-integrable sense. Okay, so that's just thing I wanted to say. And okay, that's an open question. So the natural thing would be to have a bound in the Marcinkiewicz space. Good. So how am I doing time-wise? Quite bad here. So how much time do I have? Like 5 minutes?
We started about 5 minutes late, so you have maybe 3 more minutes.
Okay. Okay. Good. Okay. So this the proof uses many ideas. So uses holomorphic motions, and that comes from the area distortion, and also from the Stala Ivani Krause-Saxman paper. The other is that maybe I explain this because it's very easy, but very important, and it's this extremality property of the Burkholder functional. So now we have the Burkholder functional, which was isotropic, rank 1 convex, and p homogeneous, and there could be many of them. Then there is this theorem that if you have two of these functionals which coincide at identity, the Burkholder functional and another one, then necessarily there is the Burkholder functional is extremal, so it has to be below all of them, and that's the proof uses that the Burkholder functional has a lot of extremals, all radial maps. Okay. So just since I only have 3 minutes, just skip this. This is one thing. Now, from the result of a Stala-Ivani Krause-Saxman, you can show that the Burkholder function satisfies the quasi-convexity inequality at the identity. So exactly our inequality, but instead of having any matrix, the matrix is A equal to the identity. Okay, so therefore it's close. This is leading to this question. And okay, this is a beautiful proof using holomorphic motions that I don't have time to explain. Maybe Isvan can tell you more. And then the other thing that we need is that we need this actually at the level of sequences. And for that, you need to use the theory of gradient jump measures. And okay. And to deal with these gradient jump measures, maybe let me put this aside. This was my first theorem. Okay, the first theorem of my thesis was deal with sequences of which were almost quasi-conformal, and to show that they could be replaced by principal maps. And my last theorem, which is here, is that you can do the same thing with K in A1, and that's it took 22 years to do it, so it should be more complicated. Anyhow, we have quasi-convexity at the identity, and then we have this extremality property. So the proof goes by defining this envelope in terms of, this is necessarily technical, I'm sorry, in terms of jump measures, and so that this envelope RP is going to be rank 1 convex, p homogeneous, and isotropic. So, and from the result of the identity plus the ideas of jump measures, you can show that the BP coincides with this envelope at the identity, and then the extremality, because this is a rank 1 isotropic, homogeneous, and blah blah, shows that they coincide anywhere. So it's a kind of a strange argument that we haven't been able to prove anything direct. Okay, and just as maybe for the more complex analysis oriented people, The classical area formula reads like the first line up here for the determinant. Then we can prove what we call the Burkholder area formula, which remember that I told you that the Burkholder functional for p equal to 2 is the determinant. And so we have this related inequality with a different constant, which is nothing but a quantitative version of a principal quasiconvexity. So principal quasiconvexity would be that this is greater than 0, but we have even a quantitative estimate. Okay, thanks for your online hospitality.
Yeah, thanks, speaker, for interesting talk. So are there any comments or questions? Can you actually show the slides with the holomorphic motion argument?
So, I mean, the idea is very interesting because so you have this deformation. You want to show that Vp of d of f is greater than Vp at the identity. So what you do is you travel from the identity map from Z to F in a neuromorphic way. So what? And then, okay, what are you gonna do? You take the corresponding Beltrami equation, and then you perturb the coefficient of holomorphically. Okay, and that I think is a brutally new idea, new way to do these things. And then you have to be very careful, and it's not easy at all how to choose this so not anything would do. You really need to choose very carefully this how to call it, holomorphic time. This holomorphic time, and then for that you need to do some business with holospheres that I think is okay. Isvan is there. I think he's the expert in doing this part.
Okay.
So,
yeah. Hi. Yeah. Thanks for the talk. A lot of different ingredients mixing nicely, but I think you showed that in some ingredient was a non-quadrature domains or something. This quadrature domains, so that comes in the area in the end or
because we proved that if that BP is or W, I can even show it here. This give me a second. Okay, so what do you get from principal quasiconvexity? These principal quasiconformal maps, you know that if this guy is quasiconvex, so I can do things in the unit disk, but principal quasiconvexity tells me that is like linear at infinity. Okay, so I have the disk here, and I have infinity there. And from quasiconvexity, it's not difficult to prove that they would satisfy this sort of inequality, okay, in the entire disk. But you want to prove the inequality, but you need to prove the inequality in the disk. And then what you need to understand is what happens in the complement of the unit disk. And then what happens is that this, remember that when we have our principal maps, they are conformal outside of the unit disk. So my function W view actually simplifies quite a lot because the distortion is 1. Okay, and then it's going to be the logarithm of the Jacobian of an honest conformal map in the boundary of the unit disk. So when you do a composition with the linear map, then you have that this unit disk becomes an ellipse, and then you have the integral of the logarithm and the complement of an ellipse of the logarithm of the Jacobian of a holomorphic function, and that's 0 because this is a quadrature domain. So it comes in proving that certain quasi-convex functions are also principal quasi-convex, and the important thing is that you don't control what happens in the complement of the unit disk from the quasi-convexity inequality, but you know that your principal maps are at least holomorphic. And then in these cases, it happens that this is 0. In the case of the Burkholder functional, this is going to be subharmonic, and again, then you need to use that these ellipses are quadrature domains. Complements of ellipses are quadrature domains. That's where.
Yeah, I see. So thank you.
Okay, other comments or questions? Well, doesn't seem to be the case, so let's thank Daniel again.
No.